All right, so we're gonna get started. Welcome everyone to the Update Structural Models in Real Time Using Machine Learning. This is an energy and data webinar. Dr. Sid Mishra and myself, Annabella Betankar, are chairs for the Energy and Data Webinar Series Committee. I will serve as your host today. Before we begin, the model of this webinar will be a 40-minute presentation, followed by a question and answer session. During the QA session, please, if you want to submit a question, put it through the Q&A box. Make sure that you're specific to what part of the presentation you're talking about. So when we go to the end and address the questions, we know exactly what you're asking. Mr. Sunil Garg is today with us to deliver this presentation. He is the founder and CEO of Data Vedic, an early stage startup specializing in consulting, big data, data analytics, machine learning, and end-to-end data ecosystems for oil and gas industry. Prior to this, he spent over 20 years establishing and growing data management, big data, and analytics business for Schlumberger. Sunil is a sought after speaker at various industry conferences and also conducts big data, machine learning, and blockchain trainings for the industry, the government, and academia. The material presented today, go to the next slide, please.
Yeah, sure.
The material presented today is copyrighted. All the rights belong to the author. We appreciate that you do not record this presentation. The recording will be provided in the Energy and Data webpage, as well as the YouTube channel, which we are using at this time for live streaming. For those not familiarized with this event, Energy and Data is a conference organized by three societies, AAPG, SEG, and SPE, meant to gather professionals from multidisciplinary teams, geoscientists and engineers from small and large oil and gas companies, academia, research and technology, to define the future of digitalization for the oil and gas industry, influenced by external sources. The next conference will be held in Austin, Texas, from the 21st through the 24th of February. We hope to see you there. In the meantime, we have prepared a whole series of webinars, and we also have open for abstracts for technical sessions. We would love to get your input into this conference. The abstract call closes August 12th, and it covers a wide variety of topics that you can see right now on the screen. Please be part of this digitalization movement and submit your abstract soon. And the next thing we would like to do is to run a poll to understand what your background is. So Sunil can adapt the presentation content as much possible to the audience that we have today. We're gonna give it another 10 seconds. Okay, we're at about 81%. I'm gonna go ahead and end the poll. And share the results. So, Sunil, it seems like the majority of the attendants today, 80%, are geoscientists, but we do have 7% reservoir engineer, 6% from drilling and production, 4% from software scientists, and 4% other domains. Okay, and with that, I'm gonna leave you with Sunil.
Yep. Thank you, Annabella. So hope everybody can hear me okay. So I will go ahead and start. So right now I put the workflow slide up there. And this is essentially what I want to show you today. And the goal of this webinar is to kind of go through the entire, I would say, process and the steps that you can use in order to build and deploy and use a successful machine learning based solution, right? We all hear about machine learning, we all hear about data analytics, but in order to get to that goal of a usable end user application, which is using machine learning, there are lots of steps that precede it. And there are also lots of steps, that are done in order to maintain those. So that's the idea of if this webinar is to kind of go through all of those steps, and machine learning would of course be one of these steps in that part. Okay. So the workflow here is, the title is the real-time update of structural models using AI. And the workflow would be that we will start with the data types, a bunch of data here, well headers, directional surveys, gamma ray logs, and formation tops. We bring all this data into a data lake. So essentially connecting all this data together. It doesn't matter, where the data may have come from. In this case, you can see that I've labeled it as it's coming from one of the fields in North Dakota, right? And in this case, we downloaded it from the regulatory website. So we bring it into our own data lake. This is where a lot of the next steps, including data cleaning, data pre-processing, essentially getting the data ready for building the machine learning workflow takes place. And once the data is ready for that, then we will go to the next step, which is looking at how to build a machine learning model in order to predict the formation tops using the gamma ray logs and the trajectories that we have taken from here. So that will be the next part. Once we look at, what are the, let's say, looking at the steps to build the machine learning model. And once the machine learning model is ready, we will validate that machine learning model, look at its various performance criteria to see if it works or doesn't work. Once we are confident of the performance, we'll look at how to deploy it so that an end user can use the solution, right? Without worrying about, in fact, whether there is any machine learning behind the scenes or not. The end user really does not know, need to know about, what kind of technology is deployed behind the scenes. All they should worry about is, are they getting reliable results? Okay, so we will look at that, and then we will open up for Q&A. So let's go ahead with the first step. So like I said, the first step is essentially gathering the data. So let me start with the bigger picture on this. So before we jump on to, let's say, gathering the data, one of the other things that I wanted to point out for you is that along with, let's say, using machine learning, which we are using in this case, in order to predict the formation tops from gamma ray logs, some of the other aspects that you will see as I walk through the various steps are, and which are key to the success of this solution, are data management and data quality management, right? How we bring the data together, how we connect it all together, how we clean it. We will also see some big data processing techniques, and I will point those out as I go through them, right? So that you can see how you can kind of, process the data, visualize the data, use this data for machine learning at scale. You will see that how to visualize the data in various forms, including, let's say a data scientist or a data engineer or a data management guy visualizing it versus, let's say, a domain expert visualizing it, right? So we'll look at all of that. And then how to deploy such a solution. So once you have built it, in order to bring it to the end user, you need to deploy it. In this case, I'm just using a hybrid deployment, which means the user interface is running in the cloud, but the data in this case, as well as the machine learning model, is hosted in our office. Right? You can use, depending on how you built the solution and what are the requirements for your solution, right? You can choose the appropriate way, basically. And at the end, basically, I will go and kind of wrap it up by, again, pointing out how an end-to-end solution is really critical for an end user to use this kind of solution. So let's now jump into the real stuff. Right. So like I said, we will start with the data, and we'll start by looking at the big picture of the data. And you will see that, on your screen, because we are doing a remote presentation, this may take just a few seconds to stream in. Once it starts getting streamed in properly, it will basically work. Okay. So we'll first look at the big picture of this in terms of data. Then we will look at the actual data we are using that work for that work. So this is essentially the big picture, right? It's kind of showing you all the data that we have brought into this data lake. And the reason I show this part is because the more your data is in the right shape, the better you are prepared for training your machine learning models. So you can see this data is all US and Canada data. So 5.7 million wells there. This is one place where some big data processing techniques come in, because of course, you cannot show all of that here. I mean, all the wells are showing there, but you have to do something in order to make sure that, the data shows up quickly basically, and all of the data could be filtered and sliced and diced the way you want. Okay? So that's the big data lake. And you can do some interactive filtering there if you want. If you wanted to, let's say, see for a particular state, you can do that as well by just clicking around. Okay? So that's the big picture. First is data. Now let's go ahead, and I in fact clicked on Texas, so you can see the entire thing filtered on the Texas. But let's go ahead and look at the specific data that we use for this workflow. Remember, our goal is to predict the formation tops using the gamma ray logs. So that's what we are going to look at, and we are going to look at that field basically from which we are taking the data. Right? So that's that Sanish field. You can see the wells arranged here in the map. You can also see in the center top, right, the North Dakota state where this field is located. And top left shows you the formation tops, right? This is the actual data. And what it is showing you is the average depth of each one of the formations across that Sanish field. Okay? And that's our goal, that's our output. So you can see that if I scroll down, it goes up to about 10,520 feet, right? So 2025 to 10,520 feet. So that's the average depth of the formations. Below that are your inputs. So first input is of course the gamma ray logs. And what you are seeing is the depth distribution of the gamma ray log for each well. So each bar or each candlestick is one well. And you can kind of, pull that and quickly see the entire field. Right? It's showing you the depth distribution, and this is showing you the depth distribution in measured depth. So you can see that lots of these are in 10,000 feet range. Some of these are in the 10,000 to 20,000 feet range. Okay. So, and you saw that your formation tops pretty much ended at 10,520. And so the reason for that discrepancy is essentially, if you look at the trajectories, this was TVD, of course, this is MD, right? These are all horizontal wells. You can see that there is about 10,000 feet of vertical section and another 10,000 feet of horizontal section in these wells approximately. Okay, so these are all long horizontals basically, and that's why you're producing formation. Typically, all the formations they pretty much end at 10,520 because that's essentially where the TVD of the wells is. Okay, and this is an oil producing field. You can see from the oil versus gas production chart, right? So majority of the production is all oil. So this is an oil producing field basically. This field has about 750 wells. That's how we started with. Out of that, I would say we had consistent data for about 250 wells. We had, in fact, data, let's say, between the logs and the formation tops and the trajectories. We had for about 450 wells, we had all the three data types, but they were not always consistent. Okay? So about 250 wells where the data was consistent, and that's basically the set of wells that we started with in order to build this solution. So now that we have looked at the data, the next part is looking at the process in order to build the machine learning model. So we have, kind of, you can say, ingested the data, brought it into a data lake, and this is the next part. We will look at what to do with this data. And this describes the entire model building process, including some data cleanup, which is included in this process itself. So you can see that there are 7 steps there. Starting with step number 1 is essentially a way to choose the data in terms of what data you will choose for building the model. Right? A typical machine learning model building process consists of splitting your data set into training, validation, and test sets. Training is the data that you will build the model on. Validation and tests are used for testing the model. Okay? So your ultimate goal is that the test data, right, with which you will test the results, right, the results should be as accurate as possible for that test, because that test data has not been used in building the model. This is the only way you can say with confidence that the model will work for your future predictions. Training can be as good as you want, right? I mean, given sufficient time, you can fit any curve to anything, basically, right? So training is essential, that a good training is essential, but that it does not guarantee that you will get good predictions, right? Both a good training as well as being able to get good results with the blind test data ensures that you will get good results in the future. Okay, so step number 1 is essentially basically looking at just selecting the data and separating out anything that is inconsistent, right? In data science terminology, typically you will hear the word outliers, right? So step 1 is kind of keeping aside the outliers. One distinction I would make with the typical machine learning workflow, we do not throw away these outliers. I'm just kind of keeping them aside right now. Okay, I will bring them back in step number 7. Then step 2 to 6 are essentially the core machine learning training steps where the model is trying to learn the gamma ray signature for each one of the formation. Okay, so step 2 to 6, and there are, you can see some of the things written there, and you can see that some of these are basically domain rules, right? For example, step 3 is just checking the strat column, right? It's not a machine learning step basically. So the domain steps are and domain validations are kind of intermixed with the machine learning model building process. Step 7 is the step by which time, right? So let's say by the end of step 6, I have a fairly good trained model. Step 7 is when we bring back all those outliers that we separated out either in step 1 or anything that got rejected in step 6. Okay, up to, from 2 to 6, let's say something got rejected due to some reason. We bring all of those back in step 7. And what we try to do at that point is looking at, are these real problems or are these issues with the data? And if there are issues with the data, we basically try to correct that data. Initially, we used to do all of this manually. Now it is built into the model, right? And this is critical basically because going forward, whenever you are developing something like this, you should always look for any opportunity that you can for automation of all these steps. Because again, cleaning of the data is very critical to the success of the model. And if you have to do that manually every time, that just does not scale basically with a lot of. Okay, so that's again a critical step. Once we figured it out, right? Once let's say we figure out that there are data issues, we can also look at how to correct those data issues and incorporate them further in the model. So that all is done in step 7. At the end of step 7 is when you have a good model. Okay, so we'll go through that process. So first thing now, when I'm looking at the model itself, right? So I looked at the overall population of my data in the form of various charts, right? I looked at the process of building the model. I also need a way to visualize that data in the way that, a particular, let's say, actor or the user wants to look at, right? And considering, for example, if you look at the attendance of this webinar, the large number of people here are geoscientists, right? So those charts give you a good idea of the data. But I'm sure your next question is, can I look at it in a cross section to get a better idea of the data, right? So the purpose of building, let's say, the domain centric views is essentially so that the domain user or the domain expert can participate in this entire process and is comfortable participating in the process. Okay, so let me quickly see. Okay, there are a couple of questions in the chat. I guess we'll look at them at the end. So let's first look at the raw data. Okay, so this is absolutely raw data. There is no machine learning that has happened here. So remember, I said there were 450 wells for which I had the logs, right? So this is just the raw data with gamma ray logs showing and the formation, right? This is the actual data. This includes all training data, test data, everything, right? This is the entire population. Okay, so that's a very quick view. And you can see there is a long horizontal scroll bar there as well, right? So you can scroll through it because these are 450 wells and it's in kind of full scale, right? You can scroll through the entire thing and can look at the entire cross section. By the way, this is one of the places where I talked about the big data processing techniques. This is one of the places that it comes into play because with normal techniques, you cannot display this large amount of data and cannot scroll through it basically with speed. Okay, so here you can, kind of go up and down horizontally and can look at the entire data set in one view. If you have a very large screen, you can also display it in one screen basically. Right? So that's raw data. And that's just the raw data from a domain expert's point of view or from a geoscientist. The next thing I want to show you is, what happens when the training is happening? What happens when the model is getting built? Okay. So when the model training is running, this is the visual way of looking at what the model is doing when it is getting trained. Okay, so first thing that you look at is the same gamma ray logs, the raw data. You can also see there are bold lines and dotted lines. Bold lines are the actual values of the formation tops. Okay. Then you see two color coded bars basically there, right? The two zones. The first one is just the actual zone between the two formation tops. Okay, between the two actual formation tops. That's just color coded so that you can look at it easily visually. The second bar is more important because that's actually telling you what the model has learned so far. Okay, so since this is a machine learning model building going on, the second bar tells you how much has the model been able to learn from the actual data. What you really ideally want is that the second bar should overlap with this first bar as much as possible. There are only two caveats to that. One is this is model building process. So you really don't want them to match 100% because if you look at the data science theory, if things match 100% in training, that means it's an overfit model. Most likely, it's an overfit model. So it will not work very well with your blind test. Okay, so you want to leave, let's say there needs to be some divergence. You don't want it to be 100%. The second caveat is if there are data issues in the actual data. Remember, I talked about some of the things before when I looked at the machine learning model building process, right? So if there are problems with the actual data, you really don't want your algorithm to learn those problems. You want your algorithm to learn the corrections to those problems or to learn the actual data, right? The corrected data. So those are the only two caveats when I don't want these to match with each other. Okay? Other than that, this is just telling you at any point during the model building process, if you look at a training cross section, it will just tell you what progress the model has made. Okay? And this screenshot itself was taken from somewhere during the model building process. This is not the final one. Okay. Next one is we will look at, how do I know the accuracy of the model itself, right? The training, like I said, given sufficient time and given sufficient horsepower, you can fit anything to anything. Okay. So the training performance is not a great way of knowing, what is your actual performance. So in order to get the accuracy of the model, what we also do is as the model is getting trained, we are also running it on the blind test data, the test data that we have set aside and which the model has never seen. So same thing here, you have the actual gamma ray log. The first bar is telling you where the actual pick is in the blind test data. The second bar is telling you what the model is able to predict. Not what the model has learned, because this is not where the training is happening, right? This is the blind test data. It is telling you this is what it is able to predict for the actual data at this point of time. These two bars, you do want them to overlap with each other. Even if they match 100%, that's great actually for you, except for one case, which is again in the blind test data. If the data has a problem, let's say if the values were wrong for the formation tops, or if the gamma ray logs were not good, right? That's the only time when you really don't want them to match. Okay. Other than that, you really want them to match 100%. So that is, so this plot is kind of showing you the progress of prediction in terms of the accuracy of the model. Okay. So that's your test cross section. I have one more, which I'm going to just quickly display, but so the reason for building this is in fact the cross section, which includes both training and test data together. Okay. And originally we used to use this kind of cross section in order to look for the data quality issues. So a geologist would sit down in front of the screen and would look at this cross section and will look at, wherever the predictions were not great, he will look at and see, why they were not great. Are there data quality issues, right? So they will try to detect that from this cross section. That was the manual way of doing it. Now that we have done the automation of that process, the only reason to do something like this or to prepare a test and training cross section is to do a quick test of that automation itself, right? So the process corrects the data and we go back to this kind of cross section and we validate some of those corrections. That is how this model has learned over a period of time as to how to correct the data automatically, right? So there is some manual validation going on at the end to make sure that the corrections that the model is doing are okay. So that's what we use this for. Okay, so that was the visual way of looking at not only the raw data, but also the progress of model building, right? And the accuracy of the model at any point of time while it is building, right? So next thing that I want to show you is, how does a data scientist know what's going on? And how does a data scientist also know, is the model training well, right? Whatever comes out as the end product model, has it trained well? And what is the accuracy of the model? right? So this is essentially a model performance dashboard that has been built on all of the statistics that are being produced by the algorithm as it is training. Okay, so this is during the training process, and at the end is when you really want to look at it, right? Once the model has finished training, that's when you really want to have a look at it and see, what it has done basically. So you can see some statistics are displayed on the left of the screen, and then we look at the various things, that are there. So first thing is looking at the summary statistics. The prediction percentage is essentially telling you out of all the formation tops that we fed into this model, whether during the training or during the blind test, right? How much is it able to predict? For example, let's say in this case, if the prediction percentage for the test data is 98.5%, it is telling you that it's not able to predict 1.5% for some good reason. Okay? And you can move that threshold. You can say, well, I want lesser accuracy, then you can increase the percentage. The next part is telling you that it found some extra tops which were not there in the training or in the blind test data. Okay, so this is part of the data quality improvement. Part of where we correct the data is we look at if there is any data missing as well. Okay, and I will show you a couple of examples of those missing data. Right? So it has ended up picking those during the model building process. The next part is a real gauge of the accuracy. So it is telling you what is the mean absolute error between the actual value of the formation tops and the predicted value. Okay, and it shows you the total, the training as well as test. And the last measure that we have there is R square. So this is a statistical measure. You can see the formula below. So closer that is to 1, better your model is. So again, you have the R square for the overall set, the training set, and the test set. Okay. All these are good ways of looking at how good your model is, but you got to have knowledge of your data. Okay, because I will show you in fact some cases where your mean absolute error, even though it is large, it may be good for you actually, because sometimes remember I said I do not want to learn the data quality mistakes. If there are data issues, I don't want to learn those. I want to learn the corrections, right? So if the mean absolute error is large, there is a possibility that you actually have wrong data or incorrect data, right? So that can be a good red flag for you to basically go and look at the data and correct the data, right? So it's not always bad to have a large mean absolute error or a low R square, right? During the process, if that helps you in building the model and refining the model, that's actually good news, right? So let's look at what else is there on this one. Right? So this is the same field. You will recognize this from the second visual we had where I was showing you the data, right? This is the same Sanish field. The yellow colored wells are the training wells. The red colored wells are the test wells. You may often hear this question from people as to how much data is required in order to train a model like this, right? Or to train any machine learning model, right? So there isn't a fixed formula. There are some thumb rules, but there isn't a fixed formula. What is more important really and what is more critical really is a good spread of the data. Because let's say if you train in one corner of that field and you are going to test in another corner, depending on the size of the field, that may or may not work very well. Right, that's why this is all spread around. You can see the training and test wells are kind of spread around. Okay. Another thing there which you see at the top is the run number. Those are just different versions of the model that we have built over a period of time, trying to refine and use these techniques basically, right? So that's also very typical during any machine learning model building process, that you will try out different iterations basically in order to get to a good model. Below that are the formations, the various formations for which we are predicting the formation tops. So that's just a list so that you can slice and dice it visually, right? Again, it is showing you the visual way of looking at the process that we are doing at the back end. Okay, so this is just a visual way of looking. Then the next chart is showing you the actual versus the predicted formation top. It's just a cross plot between the two. And then below that, you saw the mean absolute error, which was for the entire population. You also have a mean absolute error per well. What that allows you to do is to look at, if the errors are large for some particular wells, that means either the model has not learned that part well, or maybe there is some other issue. Maybe there is a data issue, right? All that is basically possible. And below that is similar chart for R square. So apart from looking at the overall R square, right, you can also look at the individual wells R square to see which well has not trained. And you see some empty area there. This is where basically the wells were missing the tops completely. That's why the R square is showing up as empty. Either there is only one top or there is no top at all, right? So that is essentially the area in which we predict a large number of these extra tops, right? So that's another technique that you can use basically to detect the missing data and then say, can I complete that missing data? Right? You can also, I mean, one of the reasons for us building this dashboard initially was for us, as we were researching this, for us to visually look at some of this data as well. So as an example, let's say, if I want to look at this in a little more detail, I just went ahead and selected a couple of formations there, okay, rather than looking at the entire data set, so that we can filter on that, right? You can see that, these things are getting filtered, and you can see here, there are two color coded formations, right? Whatever is on that line, that 45-degree line is pretty well predicted already. There are a couple of them which are outside that. For example, let's check that one. Okay, that one is showing you about 500 feet of error. Okay, that single formation top, right? That is showing you 500 feet of error, which is not good, right? If your model is, either the model is crap basically, or there is a real data quality issue there. Okay, so you can look at this in as much detail as you want, right? You can actually, zoom in into your map just to see where it was, because it zoomed in for that well basically that I selected, right? For which I selected the formation. So you can select as many wells as you want. You can select as many formations as you want in order to kind of slice and dice the data and look at it visually in terms of looking at the model performance. Okay. The overall numbers were pretty good. So I'm just going to reset this, right? So that was just so that you could look at it in one, right? So in fact, I think I zoomed in too high. So it is now getting reset. Overall numbers are still pretty good. Okay. So we go ahead and look at what was happening with some of these data quality issues, one of which I showed you just now. So when we look at the data quality issues, right, you are looking at various things. One is the validity, of course, right? Is the data correct? Which means, does the gamma ray log and the actual formation tops that we took, right? In this case, we took it from the government website, right? Were they correlated correctly? Was the interpretation done correctly? Was it reported correctly? Right? So because sometimes, the interpretation may be correct just while entering the data or while submitting the data, there may have been mistakes. Another thing that happens is, especially in US and Canada, because the wells get sold often, right? So when one company takes over wells from another company, sometimes their own interpreters will go and do the interpretation again. So in the public data, you can have many versions of data, and not all of them will match with each other. Sometimes, in fact, the data values are quite far apart. Okay, so that kind of thing can also happen. Also, you saw in the previous screen that I showed you some extra tops, which means there could be some missing data. I don't know why. Basically, it could be during the submission. It could be the company never submitted it, right? Or, it could be lost later on due to some reason, right? So all of those are different types of, I would say, data quality issues. Now, the one that I was showing you, because I've done this, many times, I kind of zoomed into this one, right? So that was the 500 feet of error. That was this formation. You see that one at the top. This is where the actual data was. And the model said this is where it should be, where the dotted line is. That's that 500 feet of error. You can also see that, there is a problem with the stat column there, right? There is a formation in between actually. Okay. So there were many ways by which we could validate that. The main way to validate whether the prediction is correct or not is to look at the gamma ray signature for that formation. So these ones, you can see that same formation here, the Cretaceous Maori. That's that same formation here. That formation is here. And in the fourth one, it's here as well, right? You can see the exact same gamma ray signature there, right? Of course, that one is definitely wrong. Here is another quick example, a smaller correction in this case. This is where the actual data had it. And this is where we predicted it should have been based on that model, right? So a small difference, basically, maybe about 50 feet of difference. These are the two exact neighbors. These are the two very close neighbors of this well. And you can see again, the same gamma ray signature there, basically, right? So those are a couple of corrections out of all the corrections that the model did. I will show you some more. So this was the case of, where we had the completely missing tops or one top. You can see for this well, this shows only one color, right? What that means is there is only one top, which, my guess was there was really nothing was picked or nothing was reported. I mean, one is just an outlier there, basically, right? Same thing here. There was only one pick reported. And what the model did during the training process and that step 7 is to basically complete that data, right? So it picked that extra data and completed it. Okay, so that's basically was another data quality step, is to complete the missing data. Okay? So we have looked at now, ingestion of the data, model building, looking at the model performance, then we looked at the data quality issues. The next step, once we are confident about the model, let's say we have corrected all these data quality issues, we see a good model performance. The next step is, so far it's basically data scientist and data management guys work. How does an end user, how does a geoscientist use it? So we look at that, how to deploy this into it and turn it into an end user solution. Okay? And now everything that I'm showing you is kind of built for demo, but there is a commercial version of it, of course, right? So there's a commercial version of this entire thing, but this is built for demo in order to show the concept basically on how some of these solutions are built. So if I deploy this model in the real-time drilling process, that is what this screen is showing. These wells have already been drilled. There is a new well getting drilled, and you can see the gamma ray log is streaming in. This is the actual data, right? And you will see whenever it detects the signature for a particular formation top, it is continuing to pick those formation tops. It has already picked 3 of those. Okay, so this is one of the uses of this model, is that during the drilling process, it will automatically pick the formation tops for you. It may or may not be 100% correct, right? Only thing is, if you are a geologist, right, this gives you at least the first cut of those tops, and you can basically adjust those, right? If you want, you can adjust those, and the next, let's say, model building iteration of this can take that feedback into consideration in order to refine that model further, right? This is how we have also refined it, basically. Okay? So that is basically picking the formation tops as the gamma ray log is streaming in. So that's basically the real use of this. We have also used it for, just improving the data quality in a completely offline scenario, right? When we originally researched this, we had a lot of data for which there were no formation tops picked at all. And this was back in 2017 and 18 when we originally built this with a different data set than this one. And in that data set, we didn't have last 2 years of data. So 2015 and 16 were completely missing. So we use this model in order to quickly pick that. Right? That could be another use of something like this, where you say, well, can I just pick this using this tool, or can I get at least the first cut of my picks using this tool? Or you have, let's say, already picked, and you said, well, can I just quickly check the quality of the picks, right? So those are all offline scenarios which you can do as well. Okay. The last part of this is essentially, what we started with. The goal was to update the structural models, right? So once you have those picks getting done automatically during the real-time drilling process, you can also update your 3D model. And here what I'm showing you is just a simulation. It is not doing it in real time, but essentially it is showing you your entire 3D model to start with, and whichever well you were drilling, that data can stream into this 3D model and can update this. Right? So what you are seeing is all the formations. You're also seeing all the trajectories there. Let me slightly zoom in and I will rotate that so you can see those horizontal wells there. Right? So you can see those horizontal sections also, and you can zoom in as much as you want basically in this. Okay? So you can zoom in, rotate it, whichever way you want to look at it. But essentially the idea there is, and again, it is not all predicted data. This is the actual and the predicted together, right? So you start with an initial version of it, whatever is your 3D model of the field. And then as the new data is streaming in, you can update that 3D model in real time as well, right? That way you can adjust your drilling process. I mean, if the 3D model is showing, well, maybe there is a chance for collision, even after you have done all your anti-collision study, right? You can do some adjustment during the drilling process, and anything else that you want to adjust during the drilling process, right? So once it is getting updated in real time, you can do a whole lot of stuff. Okay, that was the end of the process. So essentially we walked through the process of, looking at the full, let's say, big picture of the data, then looking at the data that we used for building one of these workflows, right? Then looking at the model building process. After that, we looked at the visualized the actual data, looked at the model performance. And after that, we looked at the various data quality corrections that happened during the model building and the model test process. Okay? And then at the end, we looked at how an end user can essentially use this model. So we kind of essentially walked through that, the entire workflow of starting from data source to right where an end user can start making decision or can use this model for decision. Okay? So that was my goal in order to show you, right? To show you all of these steps. My contact information is here. If you have more questions, right, you can always contact on this email, or you can also use my personal email here, right, which is sunil.garg@datavedic.com. At this point, we will open the podium for questions. I could see that there were, Q&As popping up. So I can start taking those. Annabelle, do you want to look at those, or should I look at those and start answering some of those?
I can look at those. There are several questions in different places. So the first one that we got was, how are you evolving the AI algorithms to autocorrect for bad data? And where are you getting that input from to set those boundaries?
Can you repeat that first line, Annabelle, again? Sorry, I missed a few words there.
How are you evolving the AI algorithms to autocorrect for bad data?
Okay, thank you. So, so first part, let's say before we even evolved it, right? Let's first go through the process of that, right? When we first time when we built this, and that was a different data set, like I said, we did it all manually. There was no AI algorithm or anything in order to correct the data. As we worked through that process, when we were doing it manually, we had a team which was overlooking this process and working with the geologists and saying, okay, well, how are you doing this, right? How are you doing these corrections? And their only job was to observe and automate that, right? So you can say a geologist, a data scientist, a software engineer, and a data management guy. 4 people sitting together trying to automate that and look at the various ways and the various issues that happen with the data. And you can say that 50 to 60% of those were domain rules. Another 30 to 40% were the statistical rules to kind of scale those domain rules, right? So kind of automate those manual process, right? So that is how the process started. Now, how do we evolve this further? The way we built this kind of thing is, the goal is not to get to a particular model. The goal is to perfect the technique around building this entire thing from end to end. So what we do is, to evolve this, we use different data sets. We keep on doing this with different data sets and looking at the results of that and see, is the AI algorithm lacking somewhere? An example of that would be lesser on data quality, but being able to detect the subsurface structure. Let's say in the first version of the model, there was no fault fed in. So the model would point out somewhere, let's say if there is a fault, it will point out, that the formation top is not consistent, but it does not know to label that as a fault. It does not know, where the unconformities are. So those kind of things you have to feed in during and label some of those for the training of the model. Okay, so that is how it evolves essentially. So it requires some work from the domain expert to initially, in order to label some of those and tell the model what those are, so that the model can learn from that.
All right. Couple questions about the data. One, how did you prepare the gamma ray logs? Did you normalize them, or what did you do with them to put them through the process?
Yes. So yes, normalization is a key to this, right? So yes, we did normalize them. Another thing that you want to do during that process is making sure, because remember, these were horizontal wells, and you had some gamma ray logs in the horizontal section as well, right? So you want to make sure that you're not taking only the measured depth into consideration, right? The logs came in the measured depth, but I had those trajectories, and the specific reason for having those trajectories was to make sure that we understood what the TVDs were for those wells, right, throughout that trajectory, right? So we had to basically make sure that we correlated along with the TVDs, and also making sure that you know what your elevations are, because that can make a huge difference, especially, let's say 2 different companies acquiring this data. This was quite a large field, right? There are many operators operating in that field, right? If their elevation references are not same, your data can be completely out of sync in terms of correlation. So those are some of the other key ones. So those are all domain basically related steps that have been done to this data.
All right, another question here. Did you select the training and test data sets using random selection, or was there a particular method?
Initially, it was all random, right? So no, there was no particular method. All we wanted was a good distribution. So when we let it select it randomly, we did look at it to make sure that, you know, it was not selecting from one particular corner of the field, right? But other than that, it was completely random. When we build newer versions of the model, we kind of keep that as static so that we could compare the performance of the different versions, right? Just for that performance comparison. Right? But other than that, I would say in general, in any model building process, you definitely don't want to bias it by selecting, let's say, the test and training sets yourself. At least start with some random seed, I would say.
Follow-up question on that is, how long is the process of cleaning and identifying outliers and so on to prepare the data for machine learning?
In the initial version, that took almost 3 to 4 months, in fact. Okay. It was a different data set. It was also a very large data set when we started, right? And we were doing it not exactly for the first time. Some of us in the team had done it before, but this was the first time we were doing it in an industrial manner, let's say. So this was the first, you know, deeper research basically into it. So it took us 3 to 4 months initially.
Next question is, why not use a combination of logs instead of just gamma ray to predict the tops? Would this give you a more robust model?
Yes, certainly. In fact, that was the next step on this, right? When we did this, this was the first one, right? And, you know, the purpose of showing this is again to walk you through the process, right? So yes, we have done that as well, right? So because gamma ray logs will not be able to predict all the formation tops. So you do need a combination of the logs, right? So we have used other logs, including resistivity logs, porosity logs, and density logs.
Okay. What software are you using for machine learning? And I'm not sure if this says software or if it is more what machine learning method are you using?
That's okay. I will probably try to answer both, right? And so in terms of the actual software libraries, we use Python heavily, we use TensorFlow heavily. Okay. So in this case, from a model perspective, this is a deep learning model, right? And it is using TensorFlow basically as a machine learning library, right? Of course, you know, TensorFlow is just a collection, right? So you still have to code your machine learning model basically in this case.
Okay. Are you working on ways for the AI algorithm to create missing logs in a well from adjacent wells? Fuzzy logic type method, but more advanced.
Yes, we are in fact. So we in fact have a method for that. So the way this is deployed basically, right? With the way this kind of model is used, we actually start by, before the data starts streaming in, we start by putting a synthetic which has been generated, right, for that well, because the well has not yet started drilling, right? Before the start of the drilling, we overlay synthetic there and we kind of give an idea of what the formations would look like. Okay. And then as the real data streams in, we basically adjust it to the real data. In fact, as part of these energy and data webinar series, the one that is going to come next from me will actually be on that. It's actually a class where we go through that process of, you know, generating the synthetic. Okay, so that basically class and the webinar is all focused on that workflow. And I think it is in September, I believe. I don't remember it exactly, but I think it is in September.
I'll pull it up. Have you seen the machine predict layers that are different from the subject matter expert? And how do you handle the situation?
Have we seen that? Yes, of course. You know, so in the initial versions, it would predict a lot of stuff which was not exactly matching with what the subject matter expert said. Now, I would say it matches almost 95 to 96% of the times. It actually matches the subject matter expert's opinion, right, and the interpretation. Wherever it does not match, typically, that's where the discussion starts, because if it does not match, that means there has to be a reason for that, right? One of the reasons could be that the model, there is something specific with that layer that the model has never seen before or could not expect before. Okay, so that's essentially an opportunity to discuss as a team how to refine that model.
Okay. Are you planning on development to predict ahead of the drill bit?
We have something going on around that in the research mode right now.
Okay. By presenting a mix of prediction accuracies, R2, mean absolute errors, and so on, it is not clear whether it is regression or classification.
That's a good question. In fact, I've seen this question asked only once before from me. Okay, because so if you think about what the process is, right? It is trying to predict the depths of the formation tops, right? So it's actually trying to predict a number, which is the depth of the formation tops. But the way it does it is it adopts a probabilistic mechanism. It is not only predicting the layer boundaries. It is trying to go through the entire trajectory, and after every particular, let's say, interval, it tries to predict what layer it has encountered. So it's actually a mix of regression and classification together. Okay, so that's why both the numbers were presented there. In fact, typically mean absolute error and R square, they are typically done for regression problems, right? Classification, generally you will do a confusion matrix.
If some immediate formations are not present in some wells, will the algorithm pick that?
Depends actually. Depends on what you mean by that information, right? So as an example, let's say I showed you a couple of examples of where the formation tops were not there, right? So those, yes, it can pick as long as the gamma ray signature is there, right? If the gamma ray signature itself is bad, then what you can do, right, is use the synthetic, right? Because we also, but that's a different model. So you combine the two models, you basically say, here is the synthetic, and based on that, at least give me an idea of the substrate, right? It may or may not be again, right? Because I mean, with every synthetic, there is always some uncertainty associated.
Can this model incorporate faults and other structural features, salt, for example, or is it uniquely built for structurally quiet surface?
No, it will accommodate the faults also. In fact, I mentioned that. So what it does not know, if you never labeled a fault in the data set, what it does not know is to call it a fault. It will still identify, let's say, a shifted formation, a fault, because it's taking the logs as the input, right? It's trying to learn the signature. So it will identify that it is shifted. What it will not tell you is that it's a fault. That is the reason it is shifted. So you have to label some of those if you want to really let the model say, here is a fault, you have to label some faults in there.
Okay. Will the algorithm act based on the location of the well? For example, if the well is located in a region where a particular formation is missing, eroded, will a new well in that region be conditioned accordingly?
It depends, right? So let's say you take a well far away from the region on which you have trained the model, and that's where the formation is eroded. So if it sees that gamma ray signature, yes, it will tell you. Let's take an extreme example, right? I had this trained in North Dakota. You take it to Texas, of course, it will not work properly. There are many reasons for that. One of which is, remember what it is predicting. It is not predicting the lithology. It is actually giving you the names of the formation tops with their depths, right? So the names of the formations, even if it's the same lithology, vary geographically, right? So one state will call it one, another state will call it completely different, right? So that is one of the other reasons why it may not predict accurately if you go too far, basically.
Okay. How is the model recognizing the log patterns? Is it counting the GR value, the gamma ray values, or the curve? Or is it more like an image recognition algorithm?
It is actually doing both. Okay. So the way, it is doing the signature, That's like images, but there is more it's more involved than the image, because remember, in this case, we have the actual digital data. This is built on the digital data, not just on the images. So we have the actual gamma ray values, right? So it has a bunch of different types of, let's say, specialized techniques built in, along with the image pattern recognition, basically.
Okay. What method are you using for reading log data live from the data lake to the machine learning model? And did it keep the model running all the time?
Okay. So the way, the entire flow happens, and this is kind of generic probably for everybody. When we did it absolutely the first time, at that time we downloaded the data from government website. It pretty much came in the form of LAS files, right? We loaded the data by developing a LAS parser and a loader into our data lake, and then from the data lake we read the data. Now that is an automated process, but the way it is stored in our data lake, every log point is actually stored in the data lake, right? So it's not stored as like, one curve as a blob or anything. Every log point is in our data lake, and basically the machine learning algorithm, and there is a data pipeline behind it, which is directly connected, which can read directly from that data lake using the data lake API.
Couple questions here that are related is, do you think one can use this type of approach in highly fractured areas like compressive reverse faults? And how does it handle the repeat section if heavily faulted geology?
So for the repeat section, if you have logged it, right, it will basically handle that. Okay. Now, if you have lots of, let's say, lots of different faults, unconformities, this, that, right? Frankly, the answer would be that I would really love to try that out first. Okay. Because I cannot tell you with confidence that it will work in every one of these cases without testing this properly. Right? So that's why we run it on different data sets, basically. Okay? So we are looking, we keep looking at different data sets and keep running it to see all these different things. And as we detect these and as we are able to label these, we kind of keep building and enhancing the technique itself.
Okay, another question here is there any similar work done for mineral exploration?
Good question. Very little, I would say, right? Not to the extent to which I will come and say, let me go ahead and present that work. But I have done a little bit of exploration on that, basically.
Regarding your data lake, what format do you need the data to go into? Is it Excel? Is it LAS? Is it LIS? Or would it take any format?
That's a good question, in fact, right? So what we did was we tried to, the reason it took, remember I said first time it took 3.5 months. One of the reasons for we were building these tools, basically, right? So now that we have built these tools, it really does not matter, basically. Right now, we can take in CSV, Excel, LAS, if needed, DLIS also. But so far, we have not done that, okay? But what we do is, as part of researching these machine learning workflows, you saw my initial chart of data management and all that stuff mentioned, right? A part of that is building these repeatable tools in order to ingest the data, right? The easiest way for us in this case is taking the LAS or a CSV or an Excel.
All right, and we're running out of time, so we're going to address one more question. Did you try your algorithm in the machine learning inversion? And what is the result if you did?
We haven't yet tried this one in the machine learning inversion. There are other cases where we have tried, right? And those are kind of, I would say, in the research mode, right? So some point of time I can speak about it.
All right. So I think we have addressed the majority of the questions at this time. It's we're at the top of the hour. So thank you so much, Sunil, for a wonderful presentation. We have received a lot of compliments through the Q&A and chat windows for this presentation. I want to thank everyone for your time and for joining us in this particular webinar. Don't forget that we have more webinars coming. Our next one is Machine Learning Changes Borehole Geophysics on July 6th at 9 p.m. This is a little bit out of the schedule, and we will also have another webinar at the end of July about subsurface data engineering. As Sunil was mentioning, his webinar for building an end-to-end solution using machine learning, which requires a little bit of knowledge of Python, will be September 24. Don't miss any of the webinars. I want to remind all of you that the call for abstracts is open. So if you want to be a participant on the changes in digitalization for the oil and gas industry, you're invited to submit your abstract, and we hope to see you in February in Austin at the live event. Thank you so much, everyone. Thank you so much, Sunil, again.
Thank you. And, in case people have any questions later on, like I said, my email is there. So please feel free to send me an email. Okay.
Thanks.
Thank you. Have a good day. Bye.
Bye.